Yeah, so good morning to all of you. So I hope my screen is visible. Is my screen is visible to all of you now?
Yes, sir.
Yes, sir.
Okay, great. Right. So in last class, we were discussing about the CE amplifier, right? And first we have discussed like CE amplifier without the emitter resistance, and then we have also seen like what will happen if we introduce one or a resistor at this emitter terminal, like this is RE, right? And I think we have discussed those things, in quite in quite detail, and we have seen that couple of things. Okay, I am not going to go back to those things. It is already been covered in the last class, right? So, couple of important things that we can see from here. For example, that what about the input resistance? Okay, for both cases, means with or without emitter resistor. See this input resistance, when you do not have this resistor here, it is like this. R1, R2, I mean R1 parallel R2, that you know, right? R1 parallel R2, and if you do the small signal circuit, equivalent circuit, then that R pi will also come in parallel along with this R1 and R2. So it will be equivalent is R1, R2, R pi. And this input resistance Ri is basically the resistance, right? If you look from this, from this direction, right? So the resistance offered by this base. Right. However, when you have introduced this emitter resistor Re here, then we have also seen this input resistance has been changed to this value, right? So what is this? This is again R1, R2 is going to be there, right? Because and they will be in parallel. And along with that, instead of this R pi, this term would now be changed to R pi. Maybe I can use this color here. This R pi would now change from this R pi plus 1 plus beta into Re, right? And we have discussed this exclusively in the previous class, and we have said that this is nothing but the resistance reflection rule, right? So this Re resistance would be multiplied by 1 plus beta term, and that would be added with this R pi, right? And that would give you the total input resistance if you look from this side. Fine. Okay. So now if you compare these two values, right, then obviously, okay, before we compare, let us see what are the typical values. So what is the typical value for R pi? Like, it obviously depends on the value of this beta as well as the operating point IC, right? So depending on the typical value, means if you consider the typical values of IC, then you will see the typical values of R pi would be in the range of this few kilo ohm, right? Remember, this is in few kilo ohm. So R1, this resistance will be tens of kilo ohm, say around 50, 60 or 80 kilo ohm, right? What about this R2? R2 will also be in the tens of kilo ohm, but this R2 is the value would be lower than this R1, right? Because you can see from here, this voltage drop is required just to turn on this V of B. That way we can assume that get this resistance would be higher, R1 would be higher than this R2, right? Right. So you have understood like what are the typical values. Then if you see what is the equivalent resistance without this emitter resistor, this that means for this case, then you can see then the resultant resistance will be primarily dependent or determined by this R pi, right? Because this R pi is the lowest one and all the resistance are in parallel. However, if you see from here, this resistance has been changed to R pi plus 1 plus beta into Re, and this Re would be also in kilo ohm, and that is multiplied with this 100, right? So this value is now quite high, right? So the resultant value is no longer determined by this R pi term, but rather the equivalent of this. And obviously, from this you can say that Ri in this case would be higher, right? Ri, that input resistance for this case, this would be higher. Right. So input resistance would become higher. So what is the advantage of having higher input resistance? Anyone? What is the advantage of having higher input resistance?
So the voltage drop will be more.
Voltage drop would be more. I think you are trying to mean this Vs, right? see, if we draw the equivalent circuit from this input side, an AC equivalent circuit, then it is VS, then it is RS, right? Then it is this okay, RI, right? Right. This is the input side, right? This is the base terminal, right? Not, yeah, not exactly here. This is the base terminal, but yes, this is the base terminal, right? So if you now see, if this RI is higher, then what will happen? Then uh, this VS will try to drop completely across this VI, right? So for this case, with emitter resistor, then whatever you are applying as an input signal here, the entire voltage will try to fall across this. However, for this case, okay, as this RI is lower, then there will be loading effect. Loading effect means the voltage will be divided between this RS and this input resistance here, right? And compared to this case, the VS drop across this input resistance would be lower for this case, right? So that is one advantage of having this higher input resistance. You can eliminate the loading effect. Right. At the same time, we have also seen what about the gain, right? We have seen for this case, when you do not have any register, then we have seen this gain can be given by this formula, where you can see here this third term, the numerator and denominator. If you say this RS, if you say like this value is dominating compared to RS, then you can neglect this term, right? So the total term you can, because you can say like this is 1, because if this RS is much less than this term, first term, then this total term numerator denominator equal, then the total gain would be determined by this, right? Which is a quite high number, means large value. Whereas when we are discussing the gain, the small signal gain for this circuit, so we have seen here the gain was coming in this way, right? And here we have assumed for a typical case, this RI is higher than RS, then this can be neglected to, this can be, approximated to 1. Similarly, we have seen if this term is like compared to R pi, this is higher, then beta beta case cancels, and then the gain can be approximated to minus RC by RE, right? So here we have seen this gain is dependent on GM, right? Because GM is dependent on beta. So gain is dependent on the transistor parameter, but here the gain is almost independent of transistor parameter. At the same time, we have also seen the gain is substantially reduced for this case, right? So there is a trade-off that the input resistance you are able to increase for this case, but the gain the gain is basically reducing, right? But at the same time, we have also discussed this RE is anyway required to obtain biasing stability of this. Even for the DC biasing stability, we need it, right? Along with that, thermal runaway problem that can be eliminated by the negative feedback effect introduced by this RE, right? Those things we have already discussed. But here, the moral of the story is that gain is now determined by approximated by this formula minus RC by RE. So from here, it is clear to it's quite clear that the RE value is now higher, right? Then the small signal gain is expected to be lower, right? So that way, we want that RE to be as low as possible to get a better gain, right? However, means it would be better eventually if we can eliminate the effect of RE, but that is not possible from the stability point of view, right? So let us see what we can do. So let us see for this circuit. So earlier in this circuit, we are biasing this base by this voltage divider, right? And let us say, and there only one supply voltage was there, VCC. Right, but in the next circuit, we are using two different supply voltages. I think you are also aware of this type of circuit. We have already seen this dual supply. This is plus 5 volt and minus 5 volt, right? And you need a base resistor to forward bias this emitter to base voltage, right? Or base to emitter voltage, right? And the overall circuit would look like this, right? And this is fine, right? Okay, if you take from here the output, you will get the amplified version of this VS. You will get the amplified version, but there will be phase shift, 180-degree phase shift. That is fine. But the issue is that we have seen that from here also, if you cannot calculate the gain would be RC, sorry, minus of RC by RE for this particular case, right? Again, for DC biasing stability, if you suppose need for a particular case high RE, okay, then that will significantly negatively impact the gain of small signal gain of this amplifier. So in that case, probably what we can do, instead of using one single emitter resistor, we can probably use two emitter resistors. Okay. So we can use two emitter resistors. One is this RE1 and the other one is this RE2, where this again RE1 is less than this RE2. Okay. And what we can do, we can probably, this put one capacitor across this emitter. Now, what is the effect of this capacitor, or what is the impact of using this capacitor? See, this capacitor is important because if you consider the AC circuit, or if you when you are doing the AC analysis, this capacitor would be grounded, right? This capacitor, like the capacitor would be shorted, so that way this point would be grounded, right? During AC analysis. So during AC analysis, what you are getting only the effect of RE1, right? So that way gain is now minus RC by RE1, right? Approximated gain actually. Gain is minus RC by RE1, right? Because here, because of this capacitor, this CE, right? This portion has been grounded, right? Or this is like short circuited. Right. However, during DC, what is happened? During DC, this capacitor is open circuit. So that means during DC, analysis, you have to consider the effect of both RE1 and RE2, right? Now, and during AC analysis, it is only RE1 that is going to play the play a role in your analysis. Right. So probably you can use this type of like two different emitter resistors, to achieve or to get a trade-off between the DC stability and the small signal gain. Is this part clear to all of you? I think this part I have discussed last, because I think one of you have asked me, but I think this was not discussed in a bit more detail, so I thought it will be better if we can discuss it today. Is there any doubt? I'm not getting any response from you.
No, sir.
Can you tell the use of RB?
Use of
RB.
RB. Okay, good question. So suppose if we do not have this RB, right? Then see, during DC, what is going to happen? During DC analysis, the equivalent circuit would be like this, right? During DC analysis, this is RE1, this is RE2, this is RC, this is plus 5 volt, this is minus 5 volt, and this capacitor is open, right? Right. So you have it like this. So see, this base terminal is basically floating terminal, right? If this RB is not there. So that way this transistor cannot operate, right? So you need one.
Sir, without resistor, if we can directly ground it.
Oh, instead of this resistor, you want to directly ground it. Okay. So suppose we are directly making a ground of here. Okay. Now you have to make sure that this voltage is V of BE, right? So it is not, whatever suggesting is not impossible, it's possible, you can ground it, but you have to make sure from your design that this voltage, this voltage is 0.7 volt. Okay, so that way you have to make sure the what is the current, from the DC analysis from this, so that this voltage is 0.7. That means what I am trying to say, if See, if this is 0 volt, then what should be the voltage here? Minus 0.7 volt, right? Are you getting my point?
Yes.
Yes. So if it is not 0.7 volt, if it's suppose if it's some plus value, say plus 1 volt, then again the transistor would be not be on, right? Now you have to make sure that this voltage is minus 0.7. Yeah, I think we have also done this type of analysis, right, where we have actually considered this base was grounded for this type of dual supply. It was also there in, I think, one of the practice papers, right?
Sir?
Hmm.
Sir, how come it is minus 5 volt, the emitter terminal?
This terminal, it is minus 5 volt. How come?
Yes, sir.
What
So
will
it is
you say?
grounded, so it will be 0 volt.
It is not grounded, no? Oh, sorry. I have written here, but I did not put it here. Okay. See, I have written here, na? These are dual supply voltage, right? Both plus and negative. Earlier, it was there, right? When I was editing this part, it was there, right? But later on, I forgot to mention that. Yes. So it is minus 5. Dual supply, right? Plus 5 and minus 5. Then only it is possible, right?
Sir,
Huh.
sir, if we remove RB, then sir, what will be the role of VS?
What will be the role of VS? VS is
Yes.
the, this input signal, the AC signal. This would be getting amplified. So if you do not have any VS, then at this output you will get an DC only, na?
Sir, if we remove RB, I mean, if we ground that part,
Right? If we ground,
yes, sir.
exactly, you are right. Yeah, I think earlier one of you have asked, right? What is the, means can we ground it? Yes. The point was, for if you have a DC analysis, then this circuit would work fine, right? You can ground it, it will still work. But your friend has made a very important point. Then see, we are applying this RS and we are applying here this VS, right? If this is VS, then what is the voltage? You know, this signal is basically always applied across this, right? And the no part of the signal is fitting across this base terminal, isn't it? Yes, you are right. So if we are
So
to
that
use it for an amplifier, yes.
so PS can go to ground even when RB is present. I didn't get what is the problem here if
Why
we
not?
ground.
Why not? If RB is there, then why will not get it? If RB is there, why will not get it? You explain to me.
No, sir, I didn't get the problem with the when we grounded.
Sorry, please repeat.
Sir,
Huh. Yeah, please repeat your question. I think your voice is not.
I didn't understand.
Hmm.
I didn't understand what will happen if we ground.
Oh, what will happen if it is ground? Okay. So, see, if it is grounded, if it is suppose if you shorted and if you grounded, then you have applied here VS, right? Okay. What will happen? Okay. Now, what will be the base current? What will be the base current? DC base current. DC base current that would be flowing through this, right? You are not getting this.
Yes.
Are you understanding?
Zero.
No.
Yes,
Why
sir.
zero? Oh, I have, you have done in practice paper this type of question. Then why are you now saying it is zero? Would this DC current be zero from
Yes,
here?
sir.
No, right? You have to apply,
No, sir.
you forgot. You have to apply KVL along this, B loop, right? And then you have to find if this is IB, right? Then this is, IB into 1 plus beta, right? That way you have to find what is the value of IB.
Yes.
Okay. Now see, in the AC equivalent circuit, in case of when you have applied this signal, what is happening? This signal is basically, see, this is grounded, right? So the signal is basically grounded. Okay, and this is basically going here, right? So no, VS is not been actually then applied. Is it still not clear? Guys, it is clear or not? Please let me know
So,
quickly.
sir, in the
Hmm.
AC analysis part, there will not be any signal generating.
Right, right. Because you have actually grounded this source, right?
Okay, sir. Understood.
Yeah, but for DC, it should work, right? I think if you see one of your, I think previous where the DC biasing part was there, there we have analyzed this type of circuit where the base was grounded.
Sir,
Fine, right?
can cannot the signal go to ground when RB is present?
This is saying can, but okay, but if RB is present, will is this some part of the signal is not also dropping across this?
It will go.
Right? Is it clear or it is not
Yes,
clear?
clear.
No. Okay, fine. So then, if it is clear, I think that was not difficult, previous one. So let us do one quick example. To suppose you have to design one BJT amplifier, okay, whose expected structure is, this circuit diagram is given here, and it is given that this VS, that is the input signal, is in the range of this 12 millivolt, which is a sinusoidal signal, and at this output we are expecting a sinusoidal output with an amplitude of 0.4 volt, right, at this output, and we are expecting one IE, and basically IE can be approximated to IC if you, because the base current is really zero, really close to very negligible. If the beta value is quite high, beta value is given here 100. So that way beta value is 100 times less, and that way we can say IE is close to equal to IC, and that value is approximated, means the required value is around 0.2 milliamps, and VCQ, that is a DC biasing, this Q point is expected to be around 4. So this voltage expected to be around 4 volt. Okay, beta value for this transistor is given, though it is given at some value 100, but it is also mentioned that for this type of transistor, the beta value can change from 75 to 125, and the V of value for this is given as V of BE on is given as 0.7 volt, right? So from here, you need to analyze the circuit and make a design, and you have to find what are the values, or no, primary required values of this RC, RE, and VR of this, means these two resistances. Okay, so how to approach then? Any idea?
So,
So
from the
first we'll
gain, we
solve for
get
DC.
RC by RE.
RC by RD. Okay. And here one more information. You can assume that RB value, okay, RB value expected to be quite high to control the base current, which is 100 kilo ohm. Okay. Yeah. So where from we can start this? That Vs is given, amplitude is given, V output is given, right? So that is basically the gain, right? Small signal gain. So we can write from here that this gain is given as 0.4 divided by 0.012, right? Both are in volt. So that way, if you calculate, it is coming around 33.43 volt. Okay, this is the gain. Okay, what next?
So, gain should not have unit, right?
Sorry. Excuse me. How can it be how can it have an unit where if it is a ratio of 2 units, right? Yes.
And so should it not be negative?
It will be negative. It will be negative, and that way, why I am not writing here negative, because it is well known. It is CE amplifier. CE amplifier output would be 180-degree phase shift. So that way you can write it here negative. It's fine. So let's say, okay, better to say then mod of gain. Is it okay now? Because now we are mostly interested on this magnitude, right? Fine.
Yes, sir.
Okay. So this value we have seen from the last analysis can be given by this RC by RE. Am I right? And this RE
Yes.
here is been, you can write it. Okay, again, we are writing this only the mod, so that way this.
So shouldn't it not be only RE1?
Yes,
Should
sir.
it not be only RE1?
RE1.
Are you sure?
Yes, sir.
Yes,
Because
sir.
Why?
yes, sir. So
Why?
in AC analysis, CE will be shorted.
Very good. It should be RE1 because here CE is when connected in parallel with this RE, right? So during AC analysis, CE has been grounded, CE has been shorted, so that way this point, this node is been actually grounded. So that way you will only get the effect of RE1. Very good.
Sir, I have a doubt here.
Hmm.
Sir, the potential of the bottom part of the point is minus 5 volt of RE2, and there would be no drop on RE2. So that point would also be minus 5 volts, sir. The junction of capacitor and RE2, emitter
No,
capacitor.
no.
Why, sir?
How it can be? Again, when we are doing the DC analysis, then this part is not considered, right?
Yes,
Right?
sir. And in
So
AC analysis, it is shortened.
in AC analysis shorted, then how
Yes,
can
sir.
you take minus
Okay,
5 in AC
okay. This is
analysis?
my AC.
In AC
Okay.
analysis, this is the DC supply voltage,
Yes,
right?
sir. Yes, sir.
Then
Yes,
you have to
yes.
ground it, na?
Yes, sir. Forgot, sir. Okay.
Okay. Okay. So gain is this one, RC by RE1. Very good. Okay. Now here is a couple of things that you please note. I think probably you can also notice from here. Not here, the previous one. Yeah. Notice from here. We have written the gains. This is gain without doing any approximation, and this is with approximation. See, this value, this one is obviously less than 1, right? This one. Actually, this is obviously less than 1, right? Similarly, this term, if you consider eventually, even you say like R pi is negligible, then also this term, beta by 1 plus beta would be less than 1, right? So if you are approximating the gain to be equal to minus RC by RE, or say the mod value is the only RC by RE, then basically this here you are overestimating the gain. Am I clear?
Yes, sir.
Okay. So basically you are overestimating the gain. So here in this particular design problem, you are expected to get a gain of 33.3, right? And if you were writing it or approximating the gain from this circuit to be equal to this RC by RE1, so where this RC by RE1 is actually the overestimation, right? So that way you can say to get actually around 33.3, this RC by RE1 is expected to have a higher value of 33.3. Am I right?
Yes, sir.
Yes, sir.
Sir,
Okay.
higher or lower?
Okay. Should it be higher or lower? Can you please answer to this question?
Yeah. It should be higher because the gain will be lower than this
Right.
RC by RE1.
Right. Because if you now design this circuit using this one, taking this criteria, then the gain you will be getting, that will be lower than this 33.3, because we have seen that during this approximation process we are actually overestimating the gain. Right. So it is RC by RE1 is greater than 33.3. So we have to take some value, right, to start with. Let's say this RC by RE1 is equal to 40. Okay. Now we are trying to design, okay, these values, right? And we are trying to approximate what should be the values. Later on, we can check it out whether we are getting those desired values or not. Okay, that's how we should approach when you are designing any circuit. Like we should approach from some approximation, right? Like we should know here from we can start, and then we can get some closer values. And when you get some closer value, then we can check it out and then do some fine tuning to adjust the other parameters. Okay, so it is RC by RE1. Now we are getting is close to say 40. That way we can say this RC is equal to 40 times of RE1, right? Okay. Now we are doing the DC analysis. Okay. Remember, we have still not, still not, we are doing the AC analysis as of now. Okay. So during DC analysis, if we apply one KVL, say along this loop, right? Then what we can write? This is yeah. Can you please tell me what we can write if we write and DC? If we write this KVL along this loop,
minus capital IBRB
minus IBRB plus V of BE on.
BB on
Okay. Then plus
minus IC times RE1 plus RE2
minus IC. Should it be IC or IE?
IE, sir.
IE.
Yeah,
IE. IE terms RE1 plus RE2. Then
equals minus 5.
equals
So why
minus.
shouldn't it be minus VB on?
yes, sir. It
Should
will
not
be
be
minus
minus
VB
VB
on.
on. Are you sure? Should it be minus VB on?
Yes, sir.
Yes,
Yes,
sir.
so we are taking drop as negative in this equation.
Very good. Okay. So please check whether all of you whether you are do you agree with this equation, all of you? Right? Okay.
Yes, sir.
Right. Very good. If you are agreeing, then it is very good. So here, what we can do, see, we can write IE equal to 1 plus beta times of IB, isn't it? So that way, if you write it here 1 plus beta into IB, right? So this value is known. This value is known, right? And so which values are known here? And which values are unknown here?
So RB is known.
Our V of B is known. What
B is-
about IB? Is IB
IB
known?
is known because IE
Yes,
is
IB is
known and
known because
also
IC
1
is
plus
known.
beta is known.
So yeah, IB is known. Okay. RB is known.
Yes,
Right?
yes.
Okay.
So
So
only
IE
RE1
is
plus
known.
RE2.
When IE known means IB is known right here. Okay. So here from what you will get? You will get an
We will get RE1 plus RE2.
right. You will get this RE1 plus RE2. Right? This. So if you do it, it will come to this. Right? If you solve it. Right, RE1 plus RE2, you will get some value, right? So this part is, I think, should be clear to you, right? Okay. Now, probably we can also apply KVL along this loop, right? So could you please tell me what should be the equation if we write an KVL along this from here plus 5 volt to minus 5 volt? Please quickly.
5 minus ICRC
5 minus ICRC
equal to V naught.
No, we are doing with a KVL, right? From here to here. Do we know V naught? We do not know
Yes,
V
sir.
naught. Right?
0.4 volt. 0.4 volts, sir.
Hey, V naught is a sinusoidal signal. This is again AC signal. This is not the DC.
So minus VC.
Okay,
You
sorry.
understand? This
Yes,
V naught
yes, sir,
is
yes.
given is the sinusoidal signal. So this is the AC part, not the DC part. So it is 5
Yes,
minus
sir.
ICRC minus
VC
V of CE.
VC.
Then
minus IE into RE1 plus RE2.
minus or plus? Minus, right?
Minus.
Minus.
RE1, RE2. This is equal to, or okay,
Minus 5
after
volt.
this,
-5.
should it be -5 equal to -5 or only
Yes,
-5?
equal to -5.
Equal to -5.
Equal
Ah,
to.
okay, so equal to -5, right? So here, what are the things we know? Which parameters we know here? Do we know
IC.
IC?
IC,
IC, no.
VC.
VC, do we know? No, we do
VC.
not know VC.
Yes, sir.
You know? Yes, we
Yes,
know.
sir.
It is
Yes,
given,
we
right?
know.
VC is 4 volt around. So VC we know. Okay. Do we know IE?
Yes, sir.
Yes.
Yes,
Yes.
sir.
Yes. Do we know IE? Do we know RE plus RE1
Yes.
plus RE2? Yes.
Yes.
From the
Yes, sir.
previous equation we know that. Then from here the only unknown would be this RC. So we can find RC from this equation. Is it? So if you do that, RC, say it would RC would come 9.5 kilo ohm. Okay, so that way you can find RC from here. Okay, now what should be the next step?
So find
RC by
RE1 from the
RE1.
game.
equals 40.
RC by RE, right? Then we will use this this equation, right? RC by RE1, we have taken it as 40, right? So here we know RC 9.5 kilo ohm. That way we can find RE1. So from here, if you find RE1, it would come 0.238 kilo ohm, right? So we also know the values RE1, RE2 equal to this. So that way we can also find the value of RE2. And if we do that, it would come 20.3 kilo ohm, right? So from here, you can again see the what we have discussed earlier, that RE1 would be very small, right? It is only in 238 ohms only, right? And this one is 20.3 kilo ohm, right? But during AC, this part is not being considered, right? This has been grounded. That's why you are getting a gain around 33 or 40, means from this equation it is 40, but actually expected gain is to be around 33. Again, it is mode of gain, right? Okay, so here from here we have got the required values of resistances, right? 9.5, then RC, and the values of RE1 and RE2. But the thing is that if you are really suppose ever trying to make one circuit practically, then suppose if you have come up with this 238, then if you ask, go to the shop and ask for, like, I want a resistance of 238, you might not get the actual value of 238, right? Because resistance values are type of, that way, like type of fixed. Suppose if you might have available what is 240 ohm or 220 ohm, so you have to use that, right? So depending on that, say, like I am taking the same example what has been given in your book, right? So say you have chosen RE1 to be equal to 240 ohm and RE2 is equal to 20 kilo ohm, because these values of resistances are available. Okay, and this RC, say it is 9.5, you have taken it as 10 kilo ohm. So if you have taken these values, resistance values are like this, then now you know the complete circuit. This circuit is now completely known. So from this circuit, you can find what is IC again for this. What is IC, what is IB, what is IE, everything in the DC parameters you know. If you know the DC parameter, you can find the AC parameter. If you find the AC parameter, then you can do the small signal analysis and find the gain, right? So everything you can do, right? Once you have, once you know all the values, right? So suppose you have, now you know all the values and you have done the DC analysis, So now you have a value of IC, right? And primarily you need IC to find all the AC analysis, or to find the AC parameters, right? For example, you have to find this R, pi, GM, all these things are required. You need the value of IC. So once you have the value of IC, DC IC, then you can get the small signal parameter. Then you can also find the small signal gain, right? We are not doing it here. Suppose if you have done that, and finally, then we are writing it as this. When this beta was 100, right? We have considered beta equal to 100, and what we have got is this ICQ. ICQ is around 0.201, whereas ICQ we need around 0.2 milliamps, right? Okay, again, I think I should write here the units. This is milliamps. So ICQ is 0.201, which is quite close to our expected value, right? Then what is the small signal gain? AP is basically the small signal gain. So that way, AP is, for this case, if you calculate from the small signal, it is around 26.4. Okay, 26.4. So you know that means we need and gain, required gain was around 33.3. This was the required gain mod of, right? Required, this is again mod of required gain was 33.3, but what we are getting 26.4. So obviously then you can assume or you can definitely get the idea the V out would be lower than the desired output. So V output for this case is around 0.317. This is volt, but our expected V out was how much? 0.40 volt. These things were expected, right? But what you are getting here, 0.313, right? So can you now point it out, like means where we have done something wrong and why we are seeing this discrepancy, that we are expected to get a gain of 33 and we have started with this gain of 40, right? RC by RE, like to check that overestimation issue during approximation, right? But still what we are getting gain is around 26.4. So where we have done something wrong? Any idea?
Sir, 1 plus beta into RE is of the order of R pi
1 plus beta
into RE. RE1.
1 plus beta into RE is of the order of R
R
pi.
pi.
Very good, very good, very good. See here, that's what I also wanted to point it out from here. See, this was, right? This was our earlier gain. So the gain was not from here, this one, right? This gain was minus beta RC by R pi into 1 plus beta RE into RI by RI plus RA. So you can still see the error due to this was not much. You know, if you approximate it to 1, it is not much. But if you see the error that we are introducing, if we are approximating this thing, the gain to be equal to minus RC by RE, that is huge, because here what we have said, if you are approximating this term equal to closely equal to 1, then the error is not much. But for that, to do the approximation, what we have approximated, we have approximated that this R pi is very, very less than 1 plus beta into RE, right? Then only we can neglect this R pi, right? So remember, R pi is much, much less than 1 plus beta of RE. But see, are we really getting these things here for this particular case? Let us check it out. Here, REV basically means RE1 plus RE2, right? So what is the value of RE1 plus RE2? Guys, what was the value?
Sir, here we should take only RE1.
We should take only RE1. Why? Good. Why?
We
To
have
use AC analysis.
Should we take here only RE1 or we should also consider RE2? I think all of you should respond.
So only RE1 because we are
Only
doing AC
RE1,
analysis.
yes, only RE1, because we are considering the gain, and during gain, this RE2 is actually shorted, right? So it's only the RE1 that will be, that will influence. Very good. Very good. So what is the value of RE1? It is
240 ohms.
20.3, right? No. What was the value of RE1?
240.
238.
238.
243, but we have considered it how much, right? Actual circuit 240.
240.
Okay, so it is say 240 ohm, right? Then it is 1 plus beta into 240 ohm. So can any of you calculate? And what is the value? Beta is 100. How much it is coming?
24.24 kilo ohm.
Can you tell me in terms of kilo ohm?
24.24.
Is it 24? Are you sure? So it is 100. So it just gives, yeah, 24 point. Can you say it again?
24.24.
24.2.
Okay. So 24.24 kilo ohm, right? This is 1 plus beta. What is the value of R pi? What is the value of, how can you find the value of R pi?
IC by beta VT.
IC by beta VT. So what is the value of IC? 0.2, right? 0.2, this is milliamps, right?
Beta VT by IC, sir.
Yes,
beta
sir.
VT.
Beta VT by IC.
Okay, fine. 0.026 volt. So what is the value of R pi? Please calculate and tell me. Quickly, boss, quickly. Hey, you should have a calculator always in your.
13 kilo ohm. 13 kilo ohm.
Around 13 kilo ohm, right? Okay. So if it is 13 kilo ohm, then see, earlier what we have approximated, that RE1 is much less than 1 plus beta into RE. So is this condition valid? So it is R pi is
No.
13, and here 1 plus beta into RE is 24.2, right? It's just the 50%. So this approximation is not valid, right? So we are getting that error because of this. Okay, because of this effect of RE, high value of R pi, right? Okay, so you understand like what we are why we are getting lower gain. Okay, so now tell me what can we do so that we can improve the gain still, we can still improve the gain.
Sir, we can include RPi in our calculation.
We can include R pi, but again, this R pi is dependent on R IC, right? So it again depends on the DC parameters. Okay, how can we increase the gain? It's not difficult. We can increase the gain simply by reducing this RE1 value further, isn't it?
Yes, sir.
Yes.
Okay, right. So suppose if you after that try around 150 ohm instead of 240, then you can do a quick calculation and find are we closer to the expected value or not? Whatever you are, whatever you have, we have done this exercise. You can do the similar exercise and try to find like whether you are getting the gain is closer to that or not. Now, once we have suppose achieved the value which is closer to around 33 point this is 3 the gain, right? Then I think your job is almost done, right? And finally you can take one transistor in a particular simulator, this PSpice type of simulator. Using this LT Spice, you can actually simulate this type of, make any like basic circuits, and you can simulate this circuit both in AC and in DC, and you can really find what is the total voltage here. right? So depend on what do you mean by total voltage? Total voltage is the DC voltage plus the AC voltage, right? Then if you have given one capacitor here, then at the output you will only get the AC voltage only, means the only the amplified output only. DC portion would be blocked, right? So that way, I think with this program or with this example, you have got some understanding. If some type of design related problem is given to you, you should be able to come up with the transistor value so that you can make that, you can design your particular amplifier to achieve a particular gain, right? See, this is a quite simple problem, right? But the things can be now go into much more become much more complicated. If I also say, like, for this input, for this amplifier, the input resistance would be this much, the output resistance would become this much, right? Then the things would be much more complicated, right? But if it is only in terms of gain, then the analysis is not that complex, right? I hope, yes.
Sir, why are we not considering the reactance of this capacitor in the AC analysis?
Right, very good. So for hand calculations, again, we can, for hand calculation, we are considering the impedance of this capacitance is so low compared to RS that this impedance can be neglected. Okay, otherwise the total analysis would be difficult for hand calculation. But if you are using a simulator, okay, circuit simulator, then this, the impedances, the actual impedances of these capacitors would be considered there, and the output that you are getting, that you will be obtaining at this terminal, that you can assume that that output would be very close to the a practical output, because the simulator does consider all the effects. Okay, but for hand calculation, otherwise, our analysis would become much more complicated. And
Okay, sir.
also, you cannot get the deeper understanding if the things are much complex, right? So you can first understand the things in a easier way, then you can go to a much more complex situations. Eventually, you have mentioned this point, so I would also like to mention here. See, eventually, this is an PN junction, right? Collector to base. So there should also have a capacitor in the transistor, right? Eventually, this also should have a capacitor. This is the depletion capacitor. This is the diffusion capacitor. But so far, we have neglected the effect of these capacitors as well. So probably in the next class, we will consider what is the effect of including these capacitance, but not in much more detail, but type of, for just for our understanding purpose, and how this transistor, the capacitance is related to these transistors or associated with the transistors is going to impact the gain of this amplifier. Okay, so we will see that in the next class. Okay.
Sir,
Huh.
why did you take RC by RE1 as 40? Was it given means it should be greater than 33.3, but exactly why did you take it as 40?
Yeah, so you have to start with some number, right? So you could have started with 36, right? Even starting with 30, starting with 40, see what we have got. We have got gain which is lower than the expected gain, right? So if you would have started with 36, then the gain that you would have obtained, that would be even lower than this 26. Okay, so this was type of initial guess.
Do we need to check one by one, sir?
Huh?
Do we need to check one by one, like many values?
Not one by one really. So you can suppose this is greater than this, right? So instead of taking 33 to 36, it would be better if you take a good amount of jump and go to the next place. And from, okay, one more thing. See, IC value is also was given, right? So from here, you can also estimate that the R pi value, right? R pi value would be not that way negligible, right? So the approximation that we are doing for when we are doing this approximation RC by RE1 from the big expression, then you know that we have neglected this R pi, right? But from this you can estimate the R pi value is not that way negligible, right?
So, sir, we can
So
directly consider that in the formula
Yes,
which
sir.
formula?
and find the exact relation.
Which formula?
So in the
So means we
formula
can
again,
put exact
Oh,
we
in
can
relations
the
and
put
exact
second one.
values.
Okay,
R
okay,
pi.
okay. That means you you want to directly use where is the
RC upon
formula?
R pi
You
plus.
want to use directly that formula. Okay, let us go
Yes,
for
sir.
okay, let us go there and see that if we can really do that. This is the formula, right?
Yes, sir.
Yes, sir.
Oh no, this was the yeah, this one. Yeah. So you were saying that can we directly do it from here? Okay, let's see that how we can do that. So you are saying that R pi, because this IC value is given, so you can find what is the value of R pi. Then 1 plus beta into this RF. Yes. So this is RE. Yes.
So we will take beta is almost equal to 1 plus beta,
Ha
and
ha.
then we will
Right.
get RC
Right.
by R
Because this value
by
R
beta
pi is
plus RE.
right. Right. So here you can, yeah, for this example, probably you can do that because you can estimate R pi beforehand because the IC value is given. Right. But suppose in some design, IC value was not that way given, but you are given with some other type of parameters, then it would be tricky for you, right, to find start with this R pi. Then you could have to start with this approximation only, isn't it? Okay. So this design problem, this is taking so long. I thought, see, I thought of completing this AC load line, then this example, at least these two in this class. Okay, anyway, it's going to be around. Okay, just to before we stop, just let me tell the what is the let me introduce this AC load line part to you, and we can continue in the next class from here. See, AC load line concept is we are already aware of this DC load line, right? We know that here this is IC, so and here this is V of CE. This in this plot we know how to find the DC load line. So how to do that? You apply and KVL along this path, along this loop, right? And then from that KVL you can find this DC load line. Then depending on the biasing condition, you will get an Q point definitely, right? Right. So now if this IV value is changed, this IV value can change due to this, due to the change of this supply voltages, or maybe due to the change of this AC signal, right? So suppose now you are changing the AC signal, right? So this IB is changing, suppose like this. Then this IC is also expected to change from this value to this value to this value, right? So depending on that, we have seen that the V of CEQ, right, also expected to change between these two, right? So this is true for our previous analysis where the DC equivalent circuit and AC equivalent circuit was more or less similar. What do you mean by more or less similar? Now you consider this circuit, this is a similar circuit what we have done today. See, what is the AC equivalent here? For AC equivalent, RE2 is been shorted, right? RE2 has been shorted. So only the effect of RE1 you can see. Whereas for DC, right, if you consider this loop, for DC here you are seeing both the effect of RE1 and RE2, right? But here if you consider a loop along this in the AC circuit, right, then it ends here. So the effect of RE2 is not there, right? So that way the load line when you are applying an AC signal is not be similar with that of this DC load line. So this is the DC load line. So if you now use this DC load line to predict what should be the value of change in V of CE due to the applied small signal, right? That would not be the correct way to find it. So for that, we have to find what is the AC load line. And in the next class, you will find it that AC load line would for this particular case, see, okay, for this example, you can probably quickly see from here. For this DC load line, what would be the slope? What would be the slope of this load line? Can anyone guess what would be the slope of this line, DC? Quickly.
Oh, minus 1 by R2.
Minus 1 by R2. What is R2?
RB.
RB. No. Load line का slope में RB आता है क्या? Load line always we take ना along this path, right? तो RB तो आएगा ही नहीं. It will only have this RC and REs, right? You forgot everything.
So 10 by RC plus RE.
So slope would be minus 1 by this resistance. This
RC plus
resistance.
RE1 plus RE2.
Yes. So you
It means
please
we'll have to
write this.
approximate that IE is almost equal to IC. Then we'll get this.
Yes, we are considering beta value. Beta value is higher. So that way we can approximate IC equal to IE. So RC, RE1, RE2, right? This is the slope, right? Whereas if you now for the small signal, if you see, sorry,
Sir, this is then
your voice is breaking in between. I'm not able to hear what you are saying. Please repeat. I'm not able to hear. Again, I'm not able.
So this is AC load line.
Right? This is. Yeah, means if your friends have understood, I would request them to tell me because I'm not able to understand what you are saying. Okay, maybe you can in the next class we will discuss it anyway. So here you see for if you do the AC analysis along this loop, see here only the effect of RE1 is present and RC is present. So here the slope would be equal to minus 1 by RC plus RE. See the slope has changed, right? So now the slope has changed. So that way you can also see from here that the output V of CE will also change, right? It will not follow the DC load line, but you will get a different load line for this AC circuit. So this is happening because we have introduced here these capacitors, right? This capacitor which makes the DC analysis and AC analysis the equivalent circuits are different, right? Okay, and anyway, I think we should stop here today. Okay, so we will
that one was a DC load line, right? 1 by RC plus RE.
Right. Yeah, I will answer to your question. So please, those who have a class, please feel free to leave. Okay, so we will start from here in the next class, and yeah, and yes, you have a doubt. So please ask me.
So what you drew now is that DC load line, right? Because
no. This is the DC load line. This this what is called this? You can say purple color. This purple color is the DC load line, and this green one is the AC load line.
Yes, sir.
Right, because you can see the slope will change right here because RE1 is there, na? RE2 is not there.
Yes.
Okay, so that way, you should consider the AC load line to find what will be the voltage swing and the output, not the DC load line. Okay, if you are doing it graphically. Huh? Okay, so we'll start from here to in the next class. Okay, thank you very much.
Thank you, sir.